Welcome. Today, we're going to take an in-depth look at the IC fabrication process, the essential journey of turning raw materials into the high-performance microchips that power everything from your smartphone to space exploration. As we break this process down, you'll see how advanced manufacturing techniques create the tiny, complex circuits that are at the heart of modern electronics. Integrated circuits are not just components, they're the silent engines of the digital age. Every smartphone, spacecraft, and supercomputer relies on them. But how exactly do we transform a slice of sand, pure silicon, into billions of transistors packed onto a fingernail-sized chip? Today, we're dissecting the IC fabrication process. An integrated circuit is a monolithic semiconductor device that integrates active components, like transistors and diodes, with passive components, such as resistors and capacitors, onto a single silicon substrate. This fundamental innovation redefines scalability in electronics. We're talking about integration levels ranging from small-scale to ultra-large-scale integration, millions, even billions, of transistors in one compact space. Why go through the trouble of miniaturization? Because the advantages of ICS are not incremental, they're exponential. 1. Miniaturization. By compressing more transistors into a smaller footprint, we unlock higher functional density, more logic, memory, and analog functions per square millimeter. This enables not just smaller devices, but smarter systems. Think neural engines embedded in your phone or high-speed compute cores in ultra-thin laptops. Miniaturization also drives the feasibility of edge AI, wearable tech, and biomedical implants. 2. Reliability. When we reduce the number of discrete components and soldered joints, we eliminate common mechanical failure points. A monolithic IC replaces hundreds or thousands of external connections with microscopic internal interconnects, etched and layered with nanometer precision. This inherently improves thermal stability and reduces susceptibility to vibration, fatigue, and environmental noise. 3. Cost efficiency. ICs are fabricated using batch processing, allowing hundreds of dies to be etched simultaneously on a single wafer. This amortizes fixed costs like masks and lithography steps over a massive volume, slashing the cost per unit. It's economies of scale at the quantum level, enabling $5 microcontrollers that would cost thousands if built with discrete components. 4. Performance. Signal propagation delays are governed by the RC constant of interconnects. Shorter paths within ICS reduce capacitance and inductance, allowing signals to travel faster, switch cleaner, and consume less power. This directly translates to higher clock speeds, lower heat dissipation, and better energy efficiency, critical for everything from smartphones to data centers. 5. Uniformity. In analog and mixed-signal domains, matched device characteristics are paramount. On a single silicon substrate, transistors, resistors, and capacitors can be fabricated in close proximity under identical process conditions. This level of matching is impossible to replicate with discrete components and is crucial for applications like differential amplifiers, ADCs, and PLLs, where small mismatches can lead to significant performance degradation. The fabrication of an IC is a highly intricate, multi-step process, with each step building on the last. To give you an overview, we're talking about processes like oxidation, photolithography, etching, doping, and metallization, just to name a few. The goal is to create extremely precise patterns of electrical components, often on the scale of nanometers. Let's now get into the 7 core steps of fabrication. We'll explore what each process does, how it's executed, and its implications on performance and yield. 1. Wafer preparation. Our journey begins with the silicon wafer itself. Silicon is the material of choice for the semiconductor industry because of its well-understood properties and stable performance. The wafer, typically around 200 millimeters or 300 millimeters in diameter, starts as a single crystal of silicon grown through the Czochralski process. This crystal is sliced into thin wafers, polished, and cleaned to ensure a flawless surface. After slicing, the wafer undergoes a rigorous cleaning process to remove any contaminants or particulate matter. This is crucial because even microscopic particles can negatively impact the performance of the circuit. Once clean, the wafer is ready for the next stage in the process. Oxidation. 2. Oxidation. Oxidation is one of the first steps in modifying the wafer. Here, the wafer undergoes thermal oxidation inside a high-temperature furnace. At approximately 1000 degrees Celsius, crystalline silicon reacts with either dried oxygen, O2, or steam, A2O, to grow a layer of silicon dioxide directly on the wafer surface. The reaction is straightforward. Silicon, solid, plus oxygen, gas, which gives silicon dioxide, solid, or for wet oxidation. Silicon plus 2 of H2O, which gives silicon dioxide plus 2 of hydrogen. The resulting oxide is not deposited. It's grown from the silicon substrate itself, giving it a high-quality, dense structure with strong interface properties. This layer serves multiple roles. 1. As a gate dielectric in MOSFETs. 2. A diffusion barrier during doping. 3. Or a general-purpose electrical insulator. The thickness of the oxide is controlled by time, temperature, and ambient gas composition, with dry oxidation offering superior film quality and wet oxidation offering faster growth for thicker oxides. 3. Photolithography. Now we enter the heart of microfabrication, photolithography, the process that writes the circuit's blueprint onto silicon. Photolithography doesn't create transistors directly. It defines where every subsequent process will act. It's a patterning technique that allows selective doping, etching, deposition, or oxidation. In essence, it's the semiconductor stencil. The process begins by coating the wafer with a photoresist, a light-sensitive polymer. This coating is then aligned with a photomask, which contains the desired pattern. Next comes exposure. A beam of ultraviolet light, either deep ultraviolet light at 193 m or extreme UV at 13.5 m, is projected through the mask. Where light hits the photoresist, a chemical reaction changes its solubility. Depending on whether it's a positive or negative resist, the exposed regions become either more or less soluble in developer solution. After development, the unprotected photoresist is washed away, leaving behind a finely defined pattern. This pattern serves as a mask for etching or ion implantation, effectively transferring the design from the mask to the wafer. Modern nodes push the boundaries of physics. At sub-7 in scales, feature sizes are smaller than the wavelength of light used. To get around this, we use optical tricks, phase shift masks, multiple patterning, and now extreme ultraviolet light lithography with massive reflective optics and ultra-high vacuum chambers. Photolithography is not just about resolution. It's about alignment precision, process window control, and overlay accuracy. Every nanometer matters, and the cost of error grows exponentially as feature sizes shrink. In the race for smaller, faster chips, photolithography is the technological bottleneck and the battleground of the semiconductor arms race. 4. Doping, ion implantation. Once the pattern is defined, we move to doping, which is the process of adding impurities to the silicon wafer to change its electrical properties. This is done through a technique called ion implantation. During ion implantation, ions of dopant atoms like boron, p-type, or phosphorus, n-type, are accelerated and directed at the wafer surface. These ions embed themselves into the silicon lattice, altering its conductivity. This step is crucial for forming the p-n junctions that define transistors, the fundamental building blocks of ICs. The depth and concentration of dopants can be controlled with high precision, which is critical for device performance. 5. Etching. After doping, it's time for etching. Etching is used to remove unwanted materials from the wafer surface, exposing the underlying silicon or other layers. There are two main types of etching: wet etching, which uses chemicals to dissolve material, and dry etching, which employs gases to etch patterns in a plasma environment. In the case of dry etching, materials like argon or chlorine-based gases are used to etch fine patterns into the wafer. The result is a highly precise, cleanly defined structure. Etching is used after photolithography to carve out the active regions and create the interconnections between components. 6. Deposition and planarization. Next, we begin the material deposition phase, adding critical layers like conductors, insulators, and barrier materials. There are several methods, each selected based on material, conformity, and step coverage requirements. A. Chemical vapor deposition. Chemical vapor deposition is the workhorse of IC fabrication. Here, volatile precursor gases chemically react on the wafer surface to form a solid film. Variants include 1. Low-pressure chemical vapor deposition. For conformal films like silicon nitride. 2. Plasma-enhanced chemical vapor deposition. Lower temperature, ideal for interlayer dielectrics. 3. High-density plasma chemical vapor deposition. Good for gap fill and high aspect ratio features. Chemical vapor deposition is used to deposit materials like silicon dioxide, silicon nitride, polysilicon, and even certain metal layers. B. Physical vapor deposition. In physical vapor deposition, such as sputtering, target atoms are ejected and deposited onto the wafer. It's commonly used for metal layers like aluminum or titanium nitride, though it struggles with coverage in deep trenches. C. Atomic layer deposition. For atomic scale control and excellent conformity in extreme aspect ratios, atomic layer deposition is the gold standard. It relies on self-limiting surface reactions, perfect for ultra-thin high dielectrics and barrier layers in advanced nodes. Once deposition is complete, the wafer surface often becomes topographically uneven, especially after multiple patterning steps. That's where planarization comes in. Chemical-mechanical planarization. Chemical-mechanical planarization uses a rotating pad and slurry containing abrasive particles and chemicals. It selectively removes material to produce a flat, smooth surface, crucial for multilayer lithography. Without planarization, depth of focus errors would stack up across layers, degrading yield and performance. Chemical-mechanical planarization must balance removal rate, uniformity, and selectivity, especially when transitioning between materials like oxide and metal. In total, deposition and planarization ensure that each layer is precisely formed and flat, creating the foundation for complex 3D integration, metal stacks, and advanced logic structures. 7. Metallization and packaging. Finally, we arrive at metallization, where metal layers are deposited to form the electrical interconnections between the circuit components. Metals like aluminum, tungsten, and copper are typically used for these interconnections. These metal layers are then patterned using photolithography and etching to form conductive paths on the wafer. After metallization, the wafer is diced into individual chips. Each chip is thoroughly tested to ensure its functionality before being packaged. Packaging involves encasing the chip in a protective shell with electrical contacts that allow it to interface with external devices. And there you have it. A high-level look at the 7 fundamental steps in the IC fabrication process, from wafer preparation, through oxidation, photolithography, doping, etching, deposition and planarization, metallization, and finally packaging. Each of these steps is essential in producing the highly complex, yet highly functional integrated circuits that power everything from smartphones to supercomputers. I hope this breakdown gives you a deeper appreciation of the advanced techniques involved in semiconductor manufacturing. If you have any questions or would like to dive deeper into any specific process, don't hesitate to reach out in the comments. Thanks for watching, and I look forward to seeing you in the next video.